So our next speaker is Alec Tewsley-Booth, and his talk title is Implicit Neural Representations Using Physics-Informed Neural Networks.
All right, I'm going to propose a simple experiment. I'm going to take a ball on a spring and start it bouncing. Over time, the amplitude of the oscillation is going to decrease, as you can see in the blue line. During this experiment, I'm going to take some measurements of the position as a function of time. Now, suppose I want to know the position at any time. With discrete measurements, this can be complicated. For example, what if I took a measurement at t equals 0 and another measurement at t equals 1, but I want to know the position at t equals 1/2? Or what if I want to know the velocity of the ball, which is defined as the derivative of the position? I'd have to use a low precision discrete approximation. There is another option. I could fit my data to a continuous function that is completely defined by some set of parameters. I'll feed my function through a fitting algorithm that will determine the values of the parameters that get the fit as close to the data points as possible. Now, when I want to read the position, I can just read it off of my function. It's also much easier to do things like take derivatives or integrals with a continuous function. The problem is that when I choose a function to fit, I am making some sort of implicit assumption about the shape of my data. If I know the shape really well and choose the right function, then the results I can achieve are truly remarkable. We don't usually, but that doesn't stop us. Who here is familiar with a linear regression? The problem with simple fit functions like lines is that they don't do a good job of representing complex data. Enter the implicit neural representation. You can think of a neural network as just a function with a lot of parameters. Put in perspective, the bad fits over here have 3 or 4 parameters. The neural network I'm fitting has 1,153. But all training that neural network is fitting it to the data just like any other problem. Unfortunately, you can see we still wind up with extrapolation issues. So if only there was some way to tell the neural network what shapes it's allowed to take. So neural networks rely on something called automatic differentiation because taking derivatives is a critical part of fitting. And the laws of physics are usually written in terms of derivatives. So here's our trick. We're going to use a convenient neural network, but instead of only requiring that it be close to the data, we're also going to require that its derivatives obey our equations of motion. This is where all those parameters really come in handy. In a low parameter fit, the function has to put all of those parameters to work getting as close to as many data points as it can. The 1,153 parameter neural network has parameters to spare, so it can simultaneously match the data and also obey the equations of motion. And you can see something truly remarkable happens. Because I've taken measurements on the state of the system at early times, the equations of motions let me predict the future evolution, which is essentially accurate extrapolation. So we've got convenience and accuracy. That's amazing. What's the catch? Hardware. Neural networks rely almost entirely on brute force calculation. Luckily, implicit neural representations tend to be on the small side for a neural network. And frankly, I'm happy waiting 10 minutes for a fit if it means that I don't have to spend a week looking for the right function. Thank you.